All right, guys, so we're going to continue section 4.5 notes, and now we're going to look at examples of sketching rational functions. So the first thing that we're going to do is we're going to take our function and we are going to factor it. We've talked a lot about factoring, so I'm not going to cover exactly how we're factoring it, but in order to see our removable discontinuities, or our vertical asymptotes, it's really helpful to have that in factored form. So to start, if we were to factor the numerator and take out a negative, we'd be left with 2x plus 5, x minus 4. Bottom is difference of squares. That will factor into x plus 4, x minus 4. From here, hopefully you recognize that we have the same factor in the top and the bottom. And so we call that a whole. And that means that there will be a whole when x is a positive 4. That means we can never plug in positive 4 because that would make our denominator 0. Now, if you were to try and place this whole on the graph, we're not sure where to put it, so we need to find a y value. So pretend for a second that we canceled these x minus 4s, top and bottom, and they were gone, and all we're left with is the negative 2x plus 5 over x plus 4. We're going to plug in that 4 to see what y would be if we were allowed to plug it in. And so that would be 4 plus 4 in the bottom. And so what we'll end up getting is negative 13/8, which is roughly negative 1.6. So that means at the point 4, negative 1.6, we're going to have a hole in our graph. Our graph is going to have to hop over that spot since we can never plug in 4. Now, vertical asymptotes, we are going to see that when we look at the other factor in the denominator. And so what that tells me is that we can also never plug in a negative 4. So we will have a vertical asymptote at x equals negative 4. So that's something we can draw in right away. I know that our graph is going to hop over this asymptote and also have to hop over that hole. So we have our discontinuities taken care of, but still there's a lot to this graph that we need to know before we can make a sketch that we feel confident about. Okay, so next we're going to move into x-intercepts. And so remember that an x-intercept happens when y is 0. Well, our denominator can never equal 0. I can never make this factor equal to 0 because that would make the denominator equal to 0. So to find an x-intercept, I'm going to take the other part of our numerator, set it equal to 0, and solve. And so what we'll end up getting here for our x-intercept is negative 5/2, so about negative 2.5. So I'm going to go ahead and go over here and mark that on the graph. For our y-intercept, that happens when x is equal to 0. So I'll plug in a 0 in for x. Note that you could plug 0 in to these other factors also. It just wouldn't matter because you'd end up with a negative 4 over a negative 4, which would cancel. So you can just plug it into the simplified version of that. And so what we'll end up getting is negative 5/4 for our y-intercept. So I'm going to go ahead and plot that as well on our graph. Okay, so hopefully you can kind of see what our graph is going to look like. These intercepts definitely help. But the last thing that we need to find is our non-vertical asymptotes. And so our non-vertical asymptotes tell us end behavior. They tell us that as x gets larger and larger and larger forever, heads off to infinity, what happens to our function, what happens to our output is basically what those non-vertical asymptotes do. So before we can find a non-vertical asymptote, we want to get this into mixed number form, and we do that by dividing. Again, since these x minus 4s will end up canceling, I can just divide this negative 2x plus 5 over this x plus 4, which means that I can use synthetic division. So since I'm dividing by x plus 4, we plug in a negative 4. My coefficients, be mindful that I factored out this negative. That would make my coefficients a negative 2 and a negative 5, something to be mindful of. Bring down the negative 2, multiply it by the negative 4, that gives me positive 8. Add it to the negative 5, I get 3. Remember, this is always my remainder. We take our remainder and we put it over our divisor. And so the polynomial part is this negative 2. And so now we have it in mixed number form. And again, if you remember from our notes yesterday, that negative 2 ends up telling me any non-vertical asymptotes. So that means the line y equals negative 2 will be a non-vertical asymptote. So in this case is actually horizontal asymptotes. And so I'm going to go ahead and draw that in on the graph. Okay, now from here I feel pretty confident sketching this graph. I know it's going to be super close to this asymptote, cross through this x-intercept, this y-intercept, jump over the hole, and then follow that intercept, or that asymptote, that horizontal asymptote. Note that with rational functions, we typically have two pieces to it, so I'm just going to go ahead and guess that the other piece would do something down here as well. You could always look at a graph just to verify, though. Okay, so that is the first example. So we're going to go a little bit quicker now with this second one. Again, first thing you want to do is factor what you can. So that would be x plus 2x minus 2 in the numerator. Note that the denominator is not going to factor, which means I'm not going to have anything that cancels. So we don't have a hole. We don't have a removable discontinuity. However, we could still possibly have a vertical asymptote. So that happens wherever your denominator equals 0. But if you go to figure out where your denominator equals 0, you're going to get complex solutions. So in this case, we don't have any vertical asymptotes either. Okay, so we can move on to x-intercepts. So remember, x-intercepts come from where our numerator will equal 0, which hopefully you can just kind of look at that and see that that will occur at negative 2 and positive 2. Our y-intercepts, again, we'll plug 0 in for x. So we'll have a 0 plus 2, 0 minus 2, over 0 squared plus 4. So that will end up giving us a negative 4 over a positive 4, which is negative 1. Okay, last we want to figure out, again, our non-vertical asymptotes, what's happening long term. What makes this problem a little more unique is note that we are dividing by a quadratic, and so we cannot use synthetic division in this case. We will have to use long division. And so we will put the x squared minus 4 inside, the x squared plus 4 on the outside. Ask yourself, what times x squared gives you x squared? The answer is 1. 1 times x squared is x squared. 1 times 4 is 4. And then we subtract. We'll get 0 here. Negative 4 minus 4 is negative 8. Note that we're all out of terms, so that ends up being our remainder. So mixed number form of g of x would be 1 minus 8 over our divisor, x squared plus 4. Keep in mind the part that we care about for our non-vertical asymptotes is the polynomial part, so the 1. So our non-vertical asymptote, again, is a horizontal asymptote and is at y equals 1. So we'll go ahead and draw in that asymptote. Now from here, have enough information to make a pretty good sketch. I know that the function's going to be super close to this line, cross through an x-intercept, cross through a y-intercept, cross through another x-intercept, and then be super close to that line forever. Okay, there is our second example. So lastly, our third one. Same idea, we're going to start by factoring. The top will factor into x minus 4, x minus 2, and the bottom is already just a linear term, so it won't factor. We don't have any factors in common, nothing will cancel, so we don't have a hole, no removable discontinuity. We will, however, have a vertical asymptote, so looking at the x minus 1, I know that we will have a vertical asymptote when x would be a positive 1. So I'm going to go over here and add that to our graph. Okay, x-intercepts. Hopefully you now are getting the hang of this. You could just look at the numerator for your x-intercepts and see that they will happen when x is 4 and x is 2. So look something like that. Our y-intercept happens when we plug 0 in for x. So I'm going to plug 0 into our function. We'll have 0 minus 4 times 0 minus 2 over 0 minus 1. From here we are going to get negative 8. So there's our y-intercept. And then last, we need to write this into mixed number form so we can get our non-vertical asymptotes. Since we are dividing by x minus 1, we can use synthetic division here. We have a 1. Our coefficients are 1, negative 6, and 8. Bring down the 1, multiply by 1, add to the negative 6 to get a negative 5. Times 1 is negative 5, added to 8 is a 3. So our mixed number form for g of x, I'm going to change that to a g of x instead of a y. 3 is our remainder over our divisor. Here's our polynomial part, negative 5, and then 1x. Again, the piece of this that is helpful is the polynomial part. So in this case is the 1x minus 5. And so in this case, we call this a slant asymptote. And so that slant asymptote will be at y equals x minus 5. So we're going to graph that asymptote. Keep in mind that the negative 5 is the y-intercept and the 1 is the slope. And so I'm just going to sketch a rough line. And so I know that that's kind of the end behavior of my graph. So what that means is instead of my graph heading off to infinity like we see a lot of times, it's going to shoot off. Sorry, let me take that back. Instead of it leveling off at a number as x goes off to infinity, instead of it leveling off at like a 1 or a 2 or a 0, it's just going to keep growing and growing. So as x gets bigger and bigger, y is also going to get bigger and bigger, and it's just going to keep going up. And so you can see that over here, it's going to follow this asymptote, cross through this point, follow that asymptote. And so it heads off and it gets bigger forever and ever and ever. Over here, it'll do something very similar. Note that here we have our y-intercept, so it's probably going to follow same type of shape on the other side as well. Okay, and that is it for 4.5 notes.